Hey, welcome to our video on systems of single lenses and how they work. And this is a crucial part of geometrical optics. So the two types of lenses we'll be focusing on are biconvex, which focus light towards a point, that's the top image, and biconcave, which cause light to diverge from a point, that's the bottom image. So firstly, I'd like to introduce some need-to-know concepts and variables. The principal axis is a line that is perpendicular to and passes through the center of the lens. The focal point is where all light rays parallel to the principal axis are focused. The refractive index is a measure of how much light changes direction when it propagates through a boundary between two media with differing densities. The aperture, it's a gap or opening or slit. The center of curvature is the center of the sphere that a lens's surface would make up a fraction of. That's right here on our diagram. And lastly, the radius of curvature is the radius from the center of curvature to the surface of the lens, so right over here. And pause on this if you need some more time. But moving on, P is the distance from the object to the center of the lens, which is right over here. Q is the distance of the image formed from the center of the lens, which is right over here. H is the height of the object, and yep, you guessed it, H prime is the height of the image. M is the lateral magnification of the lens.
On the screen now are the formula for lateral magnification, the lens equation, and the lens maker's formula, all of which could be useful in geometrical optics exam questions. If needed, feel free to pause the video and make a note of these.
So, how to draw a biconvex lens diagram? First, we need to pick a start point on the object. On this example, we choose the top of the arrow as our start point. Secondly, draw three light rays. The first one is parallel to the principal axis, which hits the lens axis and then goes through the focal point behind the lens. The second one goes through the center of the lens. The third one goes through the focal point in front of the lens towards the lens axis, then travel parallel to the principal axis. The arrow should be on the point where three light rays meet. In this first example, P is in the range of f to 2f, so the image is real, enlarged, and inverted. In this second example, if P is larger than 2f, image is real, reduced, and inverted. In this last situation, when P is smaller than f, image now shows on the same side of the object. The light rays need to be extended backwards, so the image is virtual, enlarged, and upright.
For a biconcave lens diagram, the light rays from the top of the object which needs to be drawn are, firstly, a ray parallel to the principal axis which hits the lens axis and then diverges upwards, which when extended back goes through the focal point in front of the lens. Secondly, a ray which goes through the center of the lens. Thirdly, a ray which when extended forwards goes through the focal point behind the lens, but then when it hits the lens axis, it travels parallel to the principal axis. The three light rays, when extended, will meet at a point. When the object is placed between the focal point and twice the focal point distance, the image formed is virtual, reduced, and upright. When the object is placed at a distance larger than twice the focal point distance, the image is also virtual, reduced, and upright.
Now we move on to lens aberrations. This is when a lens deviates from the ideal behaviour which was previously assumed, potentially due to a lens defect. There are two types of aberrations. Firstly, a chromatic aberration is when light of a lower wavelength is refracted more and gets focused nearer to the lens. As for some materials, the refractive index increases slightly for light of a lower wavelength. This can be avoided by using various materials with differing refractive indices to make a lens. As described previously, the surface of a lens makes up part of a sphere. Therefore, a larger lens would make up a larger surface of a sphere, and in this case the focal point of the lens won't remain constant across its surface. This is because the focal point is typically derived using the small angle limit, which the edges of a lens go beyond. Therefore, light refracted at the lens's edges will not go through the same focal point as light refracted near the centre of the lens, causing a blurred image to form. This is the second type of aberration known as spherical aberration. To reduce the effect of this, either the parts of the lens furthest from the lens's centre can be bent, or an aperture can be used to block out the light which would not go through the normal focal point of the lens, reducing the blurriness of the image. Thank you for taking the time to watch this video.